Hi class. Welcome to this recorded lecture on the Higgs mechanism and the Higgs boson. Now, this lecture is meant to sequence after the discussion of the unification of the electroweak forces. So you have electromagnetism, which was then unified in a quantum mechanical or quantum field theory way with the weak force, where the weak force is comprised of charge current reactions propagated by what we now know are W bosons, and neutral current interactions, the Z bosons, as well as the photon for electromagnetism. This theory was developed during the 60s, and by 1967, Weinberg, Glasgow, and Salam worked out this theory in its entirety. But there was a problem then. The problem was, and the difficulty they had to overcome, was that all the gauge bosons which propagate the weak and electromagnetic forces came out to be massless. And that would be a problem because we know they do have a mass. We know the weak force is limited in its range because of that mass of the W and Z bosons. So we needed a mechanism to work around that, and that's attributed to Peter Higgs as well as his colleagues Robert Brout and Francois Englert. So they worked out that you need a new field, now referred to as the Higgs field, and particles interact with that field. Okay, so let's start by introducing a complex valued Higgs field. We'll denote that by phi, and what I show here is the potential the potential energy, if you like, of the Higgs field that exists everywhere in space as a function of the strength of the field. And the field is shown to the right with the imaginary component of the Higgs field, and coming out of the screen, the real component. So it's a complex valued field, phi, that we're plotting the potential energy for. But it's got a funny characteristic shape. Normally, in a vacuum, you'd expect the average value of a field to be zero. Zero net electric field, zero net magnetic field, that kind of thing. But clearly with this odd shape, the minimum is not at the center. It's not at the center of a quadratic function, for example. We've given it a special shape, which I'll come to, and that has to do with spontaneous symmetry breaking. But first, let's just write down what this field looks like, this potential that we've drawn here. So this field, let me write as the potential of the field phi, okay? And that equals some parameter mu squared times the magnitude of phi quantity squared. And we'll add to that another term with a coefficient lambda with the fourth power of the magnitude of the field phi. So that is the shape of the potential. So it has a quadratic term and a quartic term. Fine. Now, if these are positive parameters, that should still have a minimum at 0. It may be steeper than a quadratic, of course, because of the quartic term, but it would have a minimum at 0. But instead, we've inverted the field, or the potential of the field at the point when phi is 0. And that is not the lowest energy configuration. How do we achieve that? Well, we can achieve that by setting mu squared less than 0. If we choose mu squared to be negative, then that's going to invert the potential at the center of this potential well. This funny shape, it kind of informally is known as the Mexican hat potential, right? It looks a bit like a sombrero. And what we can see is the minimum energy configuration is not at the center, and that's by design. That is the Higgs mechanism. And in particular, the field at the minimum right here, right? Field there, let's call that phi naught. Well, that would be, well, I've got to take out the negative of the mu squared, which is negative, mu squared over 2 lambda. But that's sort of in magnitude. We can see this is a two-dimensional potential well because it's got a real and imaginary component. Anywhere around a ring at that minimum works. So there's a complex phase we can add here, e to the I theta. And that just means anywhere around that ring can have the minimum potential. So it's a bit arbitrary. Now, what did nature choose? Nature chose something. You have to pick somewhere in this plane, and with this potential, the lowest energy configuration is not at the point where the main field is 0, but when the field has a non-zero value. So it will roll off, if you like, and lie somewhere around that circle, but it has to pick somewhere. Okay? And that's why this is referred to as spontaneous symmetry breaking. It's no longer symmetric. It's aligned at some angle, theta. That choice is not predetermined, but it has to be a choice. And that's the spontaneous part of the symmetry breaking. We broke the symmetry, even though a priori any point along the ring was equally satisfying the minimum potential. It's a bit like how ferromagnets work. The atoms in a ferromagnet want to line up their spins to minimize their energy configuration. Which direction they do so doesn't matter to some level, unless you apply an external field. But they have to choose a direction. The magnetic domains in a ferromagnet have to line up. And so that choice, again, is an example of spontaneous symmetry breaking. Okay. All right. So what was the point of doing this? Well, by having a non-zero value of the field, that means particles, the normal particles, the gauge bosons W and Z, but also the fermions, will interact with that field. And it's that interaction which generates the mass in the unified electroweak theory. So the main points here of the Higgs mechanism are that it will generate the mass of the W and Z bosons. That was the primary thing that we needed to take care of back then, because it was a great theory, except all the bosons were massless. And so their interaction with this non-zero field in vacuum leads to that mass. But you can extend it, and the Higgs field also can couple to the quarks and leptons, the fermions, and that will generate mass for those as well. We know the electron's not massless. We know the quarks and the proton are not massless. So we have to generate them some mass as well. And one other interesting consequence is that with this Higgs field, it predicts at least, at a minimum, one new scalar boson. What is scalar? Scalar is spin 0. So it generates a new particle which has no spin, and so far all the particles, the fermions have spin and the gauge bosons have spin 1. So this is new. It's a particle without spin. So it predicts that, and that's known as the Higgs boson. So that was predicted back around 1967 for this mechanism to work, but it's taken a long time experimentally to actually find that boson. So that's the prediction. Unfortunately, this electroweak unification, this theory, doesn't actually predict the mass of that. So that's why it's been a bit of a long road. Okay, so let's shift a little bit and talk about this Higgs boson, this new scalar boson. So in other words, we're going to talk about this little guy, the Higgs boson, and its coupling to particles, which provides the mass in the theory. So that Higgs boson couples to particles, and that provides the mass. And one way to kind of think of it, how does it do that? How does adding mass? Mass is somehow adding inertia to particles, right? Let's take an example from the Gators here at UF. Let's go back in time when the Gators had Tim Tebow on the team, right? When he had the football, he was a very important person on the field. All those other players, the linebackers on the opposing team, wanted to go interact with Tim Tebow. They are not going to let him go running as fast as he can down to the end zone with that ball, or throw it for that matter. So he's going to have an interaction with the field. If the opposing linebackers are the Higgs field, he's going to be slowed down. He gains inertia, right? Now, let's suppose I got on the field and I didn't even have the football. Nobody's going to care about me. I'll have no interaction with that opposing team. I'll be able to run down the field, but for not much use, of course. And so my mass would be light. So the Higgs coupling to particles defines the mass. The more important you are, the more mass you get, the more interaction. So let me put this now as a graph. Here is a plot of the coupling to a particle versus essentially the mass of that particle. And what you'll see is a line here, because by definition, the coupling must be proportional to the mass. That's what the Higgs mechanism is meant to do, and here it is applied both to gauge bosons like the W and Z, but also the fermions, right? The bottom quark, the tau lepton, the top quark over here, and the poor little muon down there. And I've overlaid some measurements, but we'll come to that in a moment. So it's that interaction which, for example, I could draw, let's say, a Z boson coming out in space. And it might radiate here a Higgs boson, okay? And this coupling here at that vertex, that's what we're plotting, and that's the coupling that gives the mass to the Z boson. This particular diagram where Z has radiated a Higgs is known as, in analogy with Bremsstrahlung, so if I can spell correctly, so let's do that, called Higgs Strahlung. It has radiated a Higgs off of the Z. And similarly for the W. But this being a Feynman diagram, you can rotate it different ways. I could have a Higgs decay, if it's massive enough, into two Z bosons. Or I could do the same with a W boson and radiate there as well. So that's the Higgs coupling. Coupling by definition is proportional to the mass. And so, we can plot here the top quark, the WZ, the bottom, and tau. And actually, the muon coupling has not been measured, so those are just based on not seeing it, the range that is allowed. Basically, it has to be below that value. Okay, so let's go ahead and move along now and talk more about the properties of the Higgs boson. Okay, so let's go ahead and discuss the Higgs boson decays and production modes. So I'm going to bring up a chart here. For many years, we didn't know what the mass of the Higgs boson was. It wasn't predicted. So experimentally, we had a tough task. This is a chart of the branching fraction of the Higgs boson on a logarithmic scale as a function of its mass. Okay? And the Higgs couples to mass, so it's going to prefer heavier particles. For example, if the Higgs is light on this end of the graph, what does it want to couple to most? It wants to couple to bottom quarks, BB bar. It doesn't couple the top quarks here because, well, that's low mass. 2 top quarks is 2 times 170 GeV, so nearly 350 GeV. So I'm going to be a Higgs way over here to the right. So the next heaviest thing would be bottom quarks, all right? Even 2 W bosons, which is this curve here, that curve, again, the W is 80 GeV, 2 of them is 160, so that's going to be suppressed at low mass, or also the same for the Z production. So at low mass, it's bottom quarks, followed by tau leptons and charm quarks. And then the poor lowly muon branching fraction you can see is quite tiny, just about 10 to the minus 4 down here. Okay, so that's the range of possibilities, and it varies because as certain branching decays or certain decays can take place, it can mix up the branching fractions. For example, once you get to higher mass, that ZZ channel can open up, or that WW channel can open up, and that kind of inverts things, right? It wants to couple the mass. Once I have heavier things like the W and Z compared to the bottom quark, well, the bottom quark gets suppressed. But the WW and ZZ take more of a role. You might wonder, well, why does it even couple to ZZ below twice 91 GeV, below 180? And that's because one of the Z's can be virtual. It can be off shell, we call it, lower mass than 91. And one can be real. Same thing for WW. So there is some probability to decay that way as you go to lower mass, but it gets more and more suppressed the more virtual you become. Now, I show a nice dashed line here that dashed line turns out to be where we now have measured, and we'll talk about it, measured the mass of the Higgs to be. We've measured it to be 125 GeV. So now, once you know the mass, you can actually, you see the Standard Model exactly predicts from this electroweak unification and the Higgs mechanism what those branching fractions are for BB bar, for the WW, for, say, taus. You've got a bit of ZZ here as well, and dimuons, for example, which is very small because they're lighter than everything else on the chart. So the Higgs is coupling the mass. That's governing sort of the ordering here on the branching fractions, where that ordering can be changed at higher mass if the Higgs were higher because other channels open up. And what you see is, especially at 125 GeV, there's a rich number of decay channels at 125. It can decay to bottom quarks, W bosons, Z bosons, tau leptons. With enough data, maybe into dimuons it's seen. And so it's very, very rich. But experimentally, as I'll come to, the cleanest signatures will be to, for example, to 2 Z bosons, 2 W bosons, and also 2 photons. Notice here that there's a 2 photon curve here that's got a branching fraction of around 10 to the minus 3, 1/1000. But wait, I said photons. What's the mass of the photon? 0, right? Wait a minute, didn't I just say Higgs couples to mass? How did that get on the curve, right? How did a massless particle couple to the Higgs? Ah, that strangeness of quantum mechanics. So, yes, Higgs couples to mass, and that provides the mass, if you like, in the theory, but it can couple indirectly to massless objects. How? Of course, through virtual particles, loops. So, for example, how do we produce a Higgs, say in proton-proton collisions at the Large Hadron Collider? Well, I can have 2 gluons from each proton. Those are massless too, like the photon. So how do I get a Higgs out here from 2 gluons? Well, I can put in a loop, this triangular loop, a heavy particle like the top quark. That's going to dominate. Higgs likes to couple to top quarks because they're heavy. Gluons will couple to top quarks because top quarks have the color charge of QCD. So no problem. It might be suppressed a bit because it's this loop in the calculation, but you can have gluons couple to the Higgs, even though the gluons are massless. All right. Likewise, how do I get to gamma-gamma? How do I get to 2 photons? Well, I turn that diagram around and replace the gluon with the photon. So here's a Higgs decay into 2 photons. Again, I put a triangular loop here. I can put the top quark, but I can also put a W in there as well. And I can have the Higgs couple via this heavy particles in the loop to 2 photons. Okay. So yes, that was kind of a tricky thing there, but the Higgs will decay to massless particles as well. All right. Now let's switch a little bit to experimentally how we can observe the Higgs boson decay. So let's go through some of the main channels which were used to discover the Higgs boson. One would be this decay to light, to 2 photons, all right, that I just mentioned. So here is an event display of a collision which is consistent with the decay into 2 photons. Now, as I'll come to, it's hard to claim that a specific collision is exactly a Higgs boson that was produced. First of all, it may not be completely unambiguous quantum mechanically, but second of all, as you'll see, there's a lot of background collisions that can emulate such a decay. But here's the signature. I expect 2 photons that are high energy, each one having roughly half the mass in energy of the Higgs. I see 2 large, these blue Lego towers are the photon energies measured in the electromagnetic calorimeter, the eCal. Now, this event display also shows charged tracks coming out, right? But there are no tracks pointing to those blue, to the blue towers here. So it's consistent with a photon. There's no charge in the photon. It's not going to ionize or create electron hole pairs in our silicon tracking system, so you don't see any tracks. So that's the signature of Higgs decaying to 2 photons. What about the 2W bosons? Those are very heavy, so it's going to want to couple to 2W bosons. Well, here's a cross-sectional view of this. These are CMS event displays, by the way. Cross-sectional view of CMS. In this case, the beam is coming into and out of the screen and collides, and then I see particles coming out. The W's here, in this case, they can decay into leptons. For example, the W might decay to an electron and an electron neutrino, or a muon and a muon neutrino. But I've got 2 W's at the Higgs couple to, so one can decay one way and one the other way, right? So here we go. I have here an energy deposit, this blue tower, which is consistent with electromagnetic energy. Now, it does have a track there pointing to it, so we think that's an electron. Then I have another charge track very close to it over here, and it's going all the way through the experiment to what's in the outer blue are the muon detectors. They're wire chambers, and they detect charged particles. And I've got something consistent with a muon out there. And they're actually going in rather the same direction, which is kind of odd, right? Because if they're in the same direction, what's balancing the momentum? How can that happen? There are some tracks in here, but they're rather soft because you can see the curvature. Well, this yellow arrow here tells us the magnitude of the momentum imbalance. And that's the signature of these W's decaying to leptons plus neutrinos. We don't ever measure the neutrinos. It gives an imbalanced momentum, and that's how we can determine this signature of the Higgs decay in the WW. Finally, let's look at the Higgs decay to ZZ, 2 heavy Z bosons. And in particular, those Z bosons also can decay to leptons. They can decay to neutrinos, but they also can decay to the charged leptons. But they would come in pairs, like E plus E minus, mu plus mu minus, tau plus tau minus. So here's an event display that is consistent with both Z's here decaying to mu plus mu minus. I have 4 tracks coming from the collision point that are consistent with being muons. They're leaving tracks in these blue muon chambers. And so this is a good signature of a Higgs decay into 4 leptons, which we think is evidence for Higgs decaying into 2 Z bosons. Now, as I said, any one event is not enough to just say, there it is, that's the Higgs boson, we've discovered it, woohoo! You really have to know what your backgrounds are and measure them and compare against what your expectations were. All right. So let me show you kind of in an animated way what it looks like as the data comes in. And we're going to look at the invariant mass of, say, Higgs to ZZ decays, Higgs to 4 leptons, this Higgs to ZZ decay. So just that channel right now as the data comes in. We know if it's a Higgs boson with a fixed mass, then I should see a preferential peak, if you like, at a specific mass. So let's look at that as the data comes in. All right, so how to discover the Higgs boson. This is what, at least from the CMS experiment point of view, what that data looks like. So here is a graph. It's plotting the 4 lepton invariant mass. I see some features showing up. The black dots with error bars, those are your data. The blue histogram is a simulation of our expected backgrounds, okay? And the data is coming in, and you can start to notice some features here, right? Way down on the far left, there is a peak. It's shaded in blue. But let's look at the mass of peak. It's a little bit below 100 GeV. In fact, I claim it's 91 GeV. That's the Z boson, but in a very rare decay where rather than decaying to 2 leptons, it decayed to 4. But it still has a mass of 91 GeV. I have another peak on the far right. Now, where is that? That's kind of a triangular shape, but it's not really very sharp. That's kind of weird. And it starts just below 200 GeV. Well, remember, I'm looking at the decay. I'm looking for Higgs to ZZ to 4 muons or 4 leptons. But I can make 2 real Z bosons, right? Should be able to do that. They each can decay to 2 leptons. What's the mass of the Z boson? It's 91 GeV. Twice that is 182. So just below 200 GeV, I might start to produce real ZZs. And that's what happens. You see the triangular parts coming up at about 180 GeV. it peaks at around 200, and then it has a spectrum falling off because it gets less and less likely to produce disease with higher invariant mass. So that's a known background, if you like, of prediction theory. But what's the thing in the middle, right? So let's go back here and let the data come in again. You know, when you get your first amount of data, and this has got a timeline if you look at the top right of the graph, 2011 there, there's not much evidence of things new. But if you look in the middle between the two peaks I talked about, 91 GeV and 180, you see something else, the thing that's being highlighted in red. That's what was new. We didn't know what mass it would come at, but that's the thing that was ultimately claimed to be the Higgs boson that was predicted. Okay, so that's what was new, and that in this channel gave the evidence for the Higgs boson, the scalar. What does the data look like with the latest amount collected? That was from when the discovery was made. We've collected more data since then at the LHC. So here's a graph showing the same thing again. Again, this was my the Z peak to 4 leptons at 91 GeV. Over here was the feature I was telling you about, the ZZ being produced without a resonance at around just below 200 GeV and then having to tail up. And then the new thing right in between, which we attribute to the Higgs. But we've looked, or the LHC experiments have looked in other channels, right? So another channel would be in Higgs into 2 photons. And that's like the signature I showed you earlier with 2 just high energy deposits with no tracks pointing to them. And so this is a graph of that, that distribution here. And there is a lot of background. There's a lot of non-resonant background. This is the invariant mass of, along this way, of the 2 photons. But I'm looking for something consistent with a single invariant mass. But I do see now this bump here. There is a little glitch on top of that smooth background. If I subtract off the background fit, that's the lower plot here. Right? So if I subtract it off, I get something consistent with 0 for my fit, except this glitch here. There is a nice clean peak there in invariant mass. And let's look at the mass. Right? It's between 120 and 130, so about 125 GeV. What is the mass over here? Oh, well, it's hard to see here, but let me just call it up. This is actually the best way to measure the mass is to use the 4 lepton decay mode. And the best measurement is 125.26 GeV with an uncertainty of about 1/4 GeV. And they're consistent, right? That mass is consistent with the mass over here, which it has to be if it's the same single particle. All right. So that's the latest data on the Higgs boson. It's definitely a clear peak. And what experiments are doing now is looking for those rare decay modes, like, for example, the Higgs to dimuon that I showed you, to learn more if this coupling is exactly as predicted by the electroweak unification theory developed in the late 60s. Okay, so just one more thing to end with. So as I said, the electroweak theory came together by 1967. But it wasn't until 2012 when the ATLAS and CMS experiments announced that evidence, that discovery of the Higgs boson that had been long sought. Nearly 50 years. So many decades went by, so many other previous accelerators looking for that Higgs boson whose mass was not predicted. Most of us in the field were getting rather discouraged. We just hadn't seen any evidence. What are we doing wrong? What is wrong with the theory? We were starting to feel like, yeah, we'll find that boson when Higgs fly. All right, that ends this lecture, and I'll see you back in class.